In a 12,470 volts primary system with an underground switch, the necessity of a ground wire running from the switch to the transformer depends on several factors, primarily the grounding configuration of the system and the presence of a grounded shield. The question involves a three-phase delta primary system where the transformer is being relocated, and the existing primary wires are now too short. The setup includes a ground wire encircling the pit for the shield of the primary wires to drain to, a ground rod inside the transformer, and the secondary terminating in a distribution panel which will be grounded as the first disconnecting means. The answer states that the ground wire in the primary from the underground switch to the transformer is not necessary because the transformer has a grounded shield. To elaborate on this, let's consider the function of each grounding element. Firstly, the ground wire encircling the pit is designed to provide a low impedance path to ground for the shields of the primary wires. This is critical for draining any fault current that might occur in the cable insulation or shield, thereby preventing hazardous voltage buildup. Secondly, the ground rod inside the transformer serves to ground the transformer tank and any internally grounded components. This ensures that the transformer itself is at ground potential, further enhancing safety. Thirdly, the grounding of the secondary at the distribution panel, being the first disconnecting means, is required by electrical codes to establish a solid ground reference for the downstream electrical system. Now, regarding the necessity of the ground wire from the underground switch to the transformer, it's important to understand the role of the grounded shield. A grounded shield is designed to provide a conductive layer around the primary conductors, which is connected to ground. This shield serves several purposes, including containing electromagnetic interference, providing a path for fault current to flow back to the source in case of insulation failure, and reducing the risk of electric shock. If the transformer has a grounded shield, this shield is already providing a low impedance path to ground for any fault current that might occur in the primary conductors. In this scenario, a separate ground wire running from the underground switch to the transformer may be redundant, provided that the shield is effectively grounded at both ends. However, it is critical to ensure that the grounding of the shield is robust and reliable. This typically involves connecting the shield to the grounding system at multiple points, including at the underground switch and at the transformer. The connections must be made using appropriate grounding connectors and conductors, and the grounding system must be designed to handle the maximum fault current that could occur. The National Electrical Code, or NEC, provides guidelines for grounding electrical systems, including transformers and cable shields. It is essential to comply with these requirements to ensure the safety and reliability of the electrical system. For example, NEC Section 250.4 A5 addresses grounding of electrical equipment and typically requires that metal enclosures and other non-current carrying metal parts of electrical equipment be grounded. NEC Section 250.4 A1 discusses the performance of electrical systems. Grounding electric systems are covered under NEC Section 250.50. It is also important to consider the specific requirements of the local utility company, as they may have additional grounding requirements beyond those specified in the NEC. Utility companies often have detailed specifications for the grounding of primary systems, and these specifications must be followed to ensure that the electrical system is compatible with the utility grid. Now, let's discuss a few scenarios to understand it better. Firstly, consider the scenario where the grounded shield is not effectively grounded. In this case, a separate ground wire from the underground switch to the transformer may be necessary to provide an alternative path to ground for fault current. This is particularly important if the shield connections are corroded or damaged, or if the grounding system is not adequately sized to handle the fault current. Secondly, consider the scenario where the primary conductors are not shielded. In this case, a separate ground wire from the underground switch to the transformer would be necessary to provide a ground reference for the primary system. This ground wire would serve to limit the voltage on the primary conductors and to provide a path for fault current to flow back to the source. Thirdly, if there are concerns about step potential or touch potential in the area around the transformer, additional grounding measures may be necessary. Step potential refers to the voltage difference between 2 points on the ground that are a step's length apart, while touch potential refers to the voltage difference between a grounded object and a person who is touching it. These potentials can be hazardous if they are high enough to cause electric shock. To mitigate the risk of step and touch potential, additional ground rods may be installed around the transformer, and these ground rods may be connected to the transformer tank into the grounding system at the underground switch. In addition, a ground grid may be installed in the area around the transformer to equalize the potential and reduce the risk of electric shock. Regarding the tape shield specifically, tape shield cables are commonly used in medium voltage power distribution systems. The tape shield consists of a thin layer of metallic tape that is wrapped around the cable insulation. This tape shield serves the same purposes as a more robust metallic shield, namely to contain electromagnetic interference, provide a path for fault current, and reduce the risk of electric shock. However, the tape shield is generally less robust than a solid metallic shield, and it is more susceptible to damage. Therefore, it is particularly important to ensure that the tape shield is effectively grounded at both ends, and that the grounding connections are well maintained. To summarize, the necessity of a ground wire from the underground switch to the transformer depends on the grounding configuration of the system, the presence of a grounded shield, and the specific requirements of the local utility company. If the transformer has a grounded shield and the shield is effectively grounded at both ends, a separate ground wire may not be necessary. However, it is essential to comply with all applicable electrical codes and utility requirements to ensure the safety and reliability of the electrical system. It's also worth mentioning that grounding systems should be inspected and tested periodically to ensure that they are functioning properly. Ground resistance testing can be used to verify that the grounding system has a low impedance path to ground. Visual inspections can be used to identify any signs of corrosion or damage to the grounding connections. If any problems are found, they should be corrected immediately to prevent electrical hazards. Furthermore, it is crucial to document the grounding system design and to maintain accurate records of all grounding system inspections and tests. This documentation can be helpful in troubleshooting grounding problems and in demonstrating compliance with electrical codes and utility requirements. Another important aspect is to consider the size of the grounding conductors. The grounding conductors must be sized to carry the maximum fault current that could occur in the primary system. The NEC provides guidelines for sizing grounding conductors, and these guidelines must be followed to ensure that the grounding system is adequately sized. In addition, the grounding conductors must be protected from physical damage. This can be accomplished by running the grounding conductors in conduit or by using shielded grounding conductors. If the grounding conductors are exposed to physical damage, they should be inspected regularly and replaced if necessary. In conclusion, while the transformer having a grounded shield suggests that a separate ground wire from the underground switch to the transformer might not be strictly necessary, it's crucial to ensure the shield is effectively grounded at both ends and complies with NEC standards and local utility specifications. Regular inspections, proper grounding conductor sizing, and documentation are vital for maintaining a safe and reliable electrical system. Always consult with a qualified electrical engineer to ensure that the grounding system is properly designed and installed. It is also important to note that the information provided here is for general guidance only and should not be used as a substitute for professional engineering advice. Electrical systems can be complex and hazardous, and it is essential to consult with a qualified professional before making any changes to an electrical system.